Thank you very much for the opportunity to speak here and for the great organization. Um, I'm going to be talking about updates on emphysema. I come from a medical physics background, and I've been working on lung density quantification as part of the Quantitative Imaging Biomarker Alliance effort. So a lot of my perception comes from that physics background. I do have some conflicts of interest because I have support from Siemens Healthcare and Polarian. First, I want to start by describing the primary density measures that are described in the literature. Some other techniques have been introduced in previous talks. The ones that have the most track record are the relative area at minus 950 Hounsfield units. I just want to make a point that these measures come from, and see if this works. These measures come from this lung density histogram, which is derived from the density values in the lung volume segmented strictly to the parenchyma. And this threshold is a fixed threshold that can then be used to delineate the regional areas that fall below that value as emphysema by this definition. A second measure that's in the literature is the PERC 15. The PERC 15 is a single Hounsfield unit number that corresponds to the volume at which the lung has 15% coverage below a specific value. And that's generally using the cumulative histogram as shown here. The PERC 15 has a couple of advantages in that it is a little bit better behaved statistically, despite the fact that it doesn't give you regional measures. I do want to highlight a couple things that were discussed yesterday. First, COPD is common comorbidity in lung cancer, and this is a recent meta-analysis of 42 studies with over 100,000 lung cancer screening patients included. And the average occurrence of emphysema in these lung cancer screening patients was 45%, with 30 to 54% of these being moderate to severe. When spirometry was included, so they also looked at airway airflow limitation as well. There were approximately 40% who fell into having, 50% who fell into having airway disease. And then of that, 65% were showing airflow limitation that had previously not been diagnosed. I also include a distribution of the proportion of emphysema by region based on this meta-analysis, which shows some interesting variations in light of this international meeting. And I want to also emphasize emphysema is associated with lung cancer diagnosis. So this is a recent paper that was published, which incorporated moderate to severe emphysema in the lung RADS scoring system. This study found that there was significant fraction of more severe emphysema at all categories of the lung RADS scoring. And in addition to that, incorporation of this additional emphysema component into the lung RADS scoring improves sensitivity for prediction of lung cancer. And then finally, I wanted to highlight something from the COPD gene study where they looked at frequency of exacerbations and likelihood of occurrence of lung cancer within an 8-year period. And this showed that with one or more exacerbations, there was an increased likelihood of lung cancer in this evaluation period, and made me wonder about whether earlier intervention to help ameliorate the COPD could impact the lung cancer progression itself. Controversial, but just something to think about. All right. All of those presentations that are papers that I just presented to you are using a visual assessment of emphysema. So what's the rationale for an automated lung density assessment? So quantitative consistency is the primary idea. And I think the principal benefit of this would be numerical assessment of longitudinal progression so that we could incorporate the increase in emphysema along with the progression of lung cancer over time, and potentially reduced radiologist workload, although that's a complicated issue. However, quantification of emphysema, as outlined in the previous talks, is a challenging problem. And the reason it's challenging is that lung density histogram is very sensitive to sources of variability. And the principal sources are these three: physiologic, patient-specific factors that primarily are driven by inconsistency of lung inflation. Second is CT dose. So we're operating in a low dose regime. And as a consequence, there's substantial image noise that contributes to the emphysema measurement. In addition, reconstruction inconsistency, including kernel choice, can influence the level of noise significantly. Body size is another factor. For larger patients, the number of X-rays detected reduces and therefore noise increases. And then a third element of variability is bias due to scanner make and model. So water-based calibration is used. Commonly, that does not include a very careful calibration in the low density regions of air and low tissue density that are associated with emphysema. And in addition to that, proprietary reconstruction kernels and scatter correction algorithms can be inconsistent across scanner vendor makes and models. So I thought I'd walk through a couple of these just to highlight which ones contribute the most to variability. So the first is the lung inflation volume, and by far is the most severe source of variability, in my opinion, for quantifying emphysema. And I'm showing an example of this on the left, or on the right, but with the left side showing an inspiratory CT lung volume that is what we would desire. However, if the coaching wasn't well done or the patient wasn't able to achieve an inspiratory CT, we would see a lower lung volume and therefore a much higher relative density. And that lung density histogram is shown here, this plot below this, indicating how the mode is shifted to higher density values and the histogram itself becomes skewed. So you can see how any of these threshold-based measures become erroneous when we're looking at a difference in lung volume like this. So there's a couple of ways to correct for this. So the field has moved towards doing retrospective corrections. The most typical is referred to as the sponge model, and it assumes the lung mass is a constant. And doing this, we can scale the density accordingly. And because I'm a physicist, I have to have one equation. This is my only equation. We can use this ratio relative to a baseline lung volume to correct the density. And this is the volume, what's commonly called as volume adjusted density. And then the subsequent components I've been talking about in the previous slide, the noise contributes to variability as well as bias. And we'll talk about those in the next two slides. So the noise is it's a problem, but it's much more benign than the lung inflation. So a consequence of noise is that this doesn't really change the mode that much, but it changes the standard deviation around the mode. And this can be remedied to some extent by nonlinear filtering and reconstruction. So iterative reconstruction methods have addressed this to some extent. And then noise measurement and modeling is also something that the field is moving towards. We can estimate the noise directly from the individual patient's scan and then correct for that noise regionally. And then the third thing is systematic bias. This is more problematic than you might expect because it does cause a systematic shift between scanner, vendor, make, and model. However, one way to address this is to use standard phantoms. And so there are efforts that have been ongoing. This is one of the principal efforts around the Quantitative Imaging Biomarker Alliance and the new QMIC, which is the extension of that organization, is to develop these standard phantoms or test objects. And we have, I'll show you one in a subsequent slide. We have several of these that enable us to look at parenchymal density and NIST qualified foam standards that have known Hounsfield units at known X-ray energies. Just to kind of point out that these corrections work. So this is data looking at the National Lung Screening Trial, in which there was a high frequency nonlinear noise reduction filter applied to the data. And the left is the raw relative area under minus 950. On the right is the normalizer corrected data. You can see that we better distinguish the three tertiles of progression based on high, medium, and low emphysema based on the survival curve data. This is one of the phantoms that we've developed as part of KIBA, and we're integrating this phantom into existing small lung nodule phantoms as part of our ongoing effort with the small lung nodule profile development with the American Lung Association. This phantom has multiple foam standards that I've outlined here, each of which has a known density that's qualified and modeled to know the Hounsfield unit value at a specific X-ray energy. We could distribute such a phantom and use this to standardize density measures across sites. This is a study that's part of the COPD gene group that I'm a contributor to, in which the variation in the lung volume was adjusted, as well as the noise, as well as the bias on the right. So what you're seeing here is baseline and 5-year follow-up data. And here is just volume adjustment. Here is correcting for all three. There is a 5-year gap, so we do expect some bias. So these, just to orient you for these Bland-Altman plots, the idea is to take the difference of measures between the two time points here against the average value. The blue line represents the bias, and the red dotted lines represent the limits of agreement. We would like the limits of agreement to be tighter around the mean value, which is true once we do these corrections. We also have a mean value that is reflective of likelihood progression of emphysema over the 5-year time span. So after introducing all of that, I thought I would walk through a couple of potential solutions. So one, I think that's maybe a no-brainer, is to improve protocol harmonization using common test objects. One benefit of this is to establish common performance specifications across sites. The cost of this is you need to adopt these metrics, and you need to convince people to adopt them, and centralized analysis may be necessary. Solution 2 would be to measure or model dose spatial resolution versus noise trade-off relationships and allow sites to make their own choices as to what that trade-off could be. The cost is that we'll have site-specific variation, but at least within and internally within a site, you'd have more consistent measures. And then solution 3 would be to optimize the reconstruction and post-processing, similar to what I walked you through in the slides presentation, in which we would optimize these and correct for these sources of variability. And the cost of this, of course, is computational overhead. An example like that, I think, was one of the earlier talks in this session that discussed the idea of cluster analysis and multiple reconstructions for one acquisition that would take different kernel types and emphasize a smoother kernel for emphysema and a higher resolution kernel for the small lung nodule measurement. I think that's a solution, but it does include additional images and processor time, and likely need for centralized analysis if we were to do this across harmonization across sites. So concluding, COPD with emphysema and airflow obstruction is a common comorbidity in lung cancer. Quantifying emphysema can improve prediction of lung cancer outcomes and offer potential for earlier intervention. Challenges to incorporating emphysema into lung cancer screening include potential radiologist workload, high degree of variability for automated measurements, as I outlined in detail. And then solutions for automated analysis on horizon, I think, include acquisition harmonization using the test objects that I talked about, and then perhaps centralized reconstruction and post-processing to noise model and correct for sources of variability using potential AI solutions. And thank you for your attention.